Okay, let's start this afternoon session, which is dedicated to fundamental physics. So you will hear here three different talks, different topics, one on clock experiments from space, gravitational waves detection on the moon, and laser ranging experiments to the moon. The topic is how to use these instruments and measurements to test fundamental physics. So the first speaker is Christophe Salomon, and he will report about the ESA mission.
Do you hear me like this? Good. So welcome to this afternoon session. I'm happy to report on the status of the ESA mission. ESA meaning Atomic Clock Ensemble in Space. And the title is Ready for Launch. Indeed, the launch is planned for April 2nd, 2025, after a long development stage. And we are all excited about the possibility to do interesting physics with these instruments once launched. So I will give you a little description of the mission, then describe the scientific objectives and how we are going to address them during the mission. So just for the non-specialist, ESAs actually will use the three main characteristics of Earth orbiting satellites. The first thing is that it is a microgravity environment. And in this condition, we will operate a laser-cooled clock, cesium clock, which is at the basis of the international definition of the time unit, the seconds. But we will use laser-cooled atoms at a microkelvin temperature to operate this clock in conditions which are very different from the Earth's operation. On Earth, we use an atomic fountain. We launch the atom up and down and measure, essentially do spectroscopy on this cesium transition. In microgravity, as you will see on some of the later slides, we are going to launch the atom very slowly into a microwave cavity to make this spectroscopy experiment. And hence, we expect a very interesting accuracy for this clock that will be used to make fundamental physics tests. The prominent one, the most prominent one, being a test of the Einstein redshift, the clock gravitational shift, that uses a second advantage of Earth orbiting satellite is that the gravitational potential at 400 kilometers, the International Space Station orbit, is different from the gravitational potential on the Earth. And finally, as is obvious, the ISS is orbiting around the Earth and will pass above the national metrology laboratories, which are developing highly accurate microwave and optical clocks on the ground, and ESAs will bring the capacity to compare these clocks together during the mission duration. So let me start by showing you the flight payload. This is the ESA's general view. It is about slightly less than a cubic meter. The longest direction is about 1 meter. The total mass is 227 kilograms and total power 450 watts. And in this, this is essentially a base plate on which you have two atomic clocks, the cold atom clocks I was just describing, and a hydrogen maser called SHM on this slide, space hydrogen maser, which will act as a flywheel, continuously operating. It's an active clock. It emits a signal, and it will serve to assess the accuracy of the cesium atomic clock. And to complement this, there is an onboard computer, and also on top of this slide, you see, I have no pointer here, but maybe here is a pointer. No. Anyway, so on top of this platform, you see microwave antennas operating in the S-band and Ku band to connect the timescale of the clocks realized on board the ISS with the timescales realized on the ground in a network of ground stations. There is also a GNSS antenna to do the precise orbit determination, and also a link which is in the visual part of the spectrum, a laser link, ELT, European Laser Time Transfer, that sends picosecond pulses of light, which are timed when they arrive at the ISS, and a corner cube, so that you have the back and forth a signal and the one-way transit time from which you can compare the two time scales, one on the ground and one in space. So the overall mission concept is as follows. This will be launched by SpaceX, then on the Dragon Flyer. With the robotic arm, it will be fixed on the ISS, on the Columbus module, on the Express palette, which is on the top left here, nadir pointing, so that we can exchange these electromagnetic signals with the ground. And on the ground, these signals will be received and emitted from the parabola and the radomes that you see here in the microwave domain, which are each connected to a set of ultra-stable clocks which operate in the visible or microwave part of the spectrum. And on the left part, you have the laser link, so you have a laser station which can emit photons toward the ISS, reflected by the corner cube, and detected on board the ISS. Everything will be operated by the CADMOS in Toulouse, at CNES Toulouse, and going to COL-CC and then to NASA Control Center of the ISS. So speaking of clocks, let me introduce the specification and the goal of the clock stability, and I should say instability, that you see on this graph. So on the left, you see the instability of the clocks as a function of time. The horizontal axis is the time duration, and you see the black line is the specification in space for Pharaoh, which starts at 1×10⁻13 at 1 second, going down to 1×10⁻16 at 10 days of averaging time. So the red arrow shows the 1 day at typically 10 to the 5 seconds, and 10 to the 6 seconds is about 10 days. So it goes to 1×10⁻16 in about 10 days of averaging. The red curve is the space hydrogen maser specification in red. So you see it's better than the Pharaoh clock until 1000 seconds. And this is why we use this clock to compare and to study the systematic effects of the Pharaoh clocks by changing the atom number density, launch velocity, and everything, and I show you that in more detail later. So you see that the ESA clock signal is a composite signal which takes the best of the short-term stability of the hydrogen maser and the long-term stability of the Pharaoh clock. And so this is a stability in the frequency domain. How do you compare this into stability of the time scale? So here you see the relation between the Allen standard deviation, so the residual frequency fluctuation in frequency space, translated into time fluctuation for the time scale. Here is the formula of sigma of tau. Essentially, you multiply, apart from a numerical factor, by tau, the Allen standard deviation that I've shown on the previous slides. And so you see in black, it's a slope tau plus 1/2, because the stability was going down in frequency by tau minus 1/2. Now it's going down up. It's going up as a tau plus 1/2. And the specification is a yellow curve, which we said that we want to measure the clock with a negligible contribution of the time transfer system in order to read the Pharaoh clock correctly. And so you see the yellow curve is a specification. It has a minimum at one single pass of the ISS between 300 and 400 seconds. This is a visibility period that you have on the given ground terminal of the ISS, and there it is below 1 picosecond of residual fluctuation. And then when you average, you can lose a few picoseconds, but still you should stay within 7 picoseconds at 10 days of averaging time. And this is the target for the scientific objectives of the ESA mission. So the microwave link actually operates right now in this condition. On a single pass, the microwave link specification is much better, even in the dynamic pass, where you have a large Doppler effect, actually, because of the relative motion of the ISS and the ground terminal. And this specification is well met in the, for a single pass. And so let me show you one of the graphs here, where you see you have a common clock. This signal is sent in a device, an EGSE device, which mimics the Doppler effect, both on the uplink and the downlink. And here you see what we call the two-way combination, where it removes the residual Doppler, this Doppler change, as a function of time during a single pass, typically 300 seconds. So you see that the residuals are here in the range of 1 to a few picoseconds. You see more noise at early times because the pointing and the laser power, the microwave link power is low on the horizon. There is more absorption, so you see more noise. And then near zenith, at the center of the graph, you have a noise which amounts to, at this integration rate, typically 1 picosecond. And then when you go to horizon in the back, you have again more noise on the time transfer. So at the bottom, you see the specification in yellow and the measured Allen standard deviation. And as I said before, on the single pass, this is very good. This is much better in this test. So on a single pass. Now, when you repeat this measurement over one day for 25 successive passes, you see on the left the typical phase fluctuations, which are peak to peak, typically 20 picoseconds at this sampling rate. And here, 3 types of attitude have been low horizon, mid zenith, and zenith, and you see that they are all relatively consistent with a zero phase phase fluctuation. And then you can plot the Allen standard deviation in time, which is the bottom right spectrum here, where you see the green curve is when you average over 25 successive passes spread over one day. So you see the more longer-term stability. And so the green curve is the stability of the phase of the code, which is a modulated code at 100 megachip. And you see that it is already quite good. So it is near the specification for the carrier phase, which is the upwards going slope that I've shown before. And so even the carrier phase is quite stable, and even the code phase is quite stable, and the carrier phase measurements are ongoing. It should be below this green curve. And this is even without correction for amplitude and phase modulation. So this is just a few words on the current status of microwave link. These measurements are going on right now and have been taken in the last weeks. So we look forward to see the final performance that can be achieved as measured on the ground and expected in space. Now, a few words about the payload. This summer, the ESA's platform has experienced a vibration test, a thermal vacuum test. Here you see the whole platform on the shaker on the left, and the big chamber where temperature and vacuum has been applied. Everything has survived all these steps nicely. You see at the bottom EMC test, electromagnetic compatibility test of the chamber. And so far, this has been excellent. So we are quite confident that the platform will operate well in space, even in presence of vibrations during launch. So this was for the space segment. And on the ground, we have 7, we call it MWL, so microwave link terminals located on 3 different continents, 2 in the US, 4 in Europe, at CIRT, PTB, VETSEL, NPL in UK. one in Japan, and plus one mobile terminal that we will bring to interesting places in order to compare either with a laser link or to other national metrology laboratories interested to host this microwave link terminal to contribute to the global network of ground clocks and their comparisons. So now a few words about the key element of the ESA's clock ensemble, the Pharaoh clock. Before saying that, let me show you that we have also a few laser time transfer laser stations on the ground. We have about 4 or 5 now which are interested in contributing for the laser ranging campaign here. So the Pharaoh clock here is an image of the cesium tubes, which on Earth here is horizontal, but during test it is vertical, otherwise the cold atom will simply fall down. So during the test on the ground, the cesium tube is vertical, and you launch the atoms upwards in the tube. You see the laser bench, which is in the shielded on the left bottom. And Pharaoh has been delivered to ESA 10 years ago already, and we are happy to see that it is still working nicely today, except that as Luigi told me a few minutes ago, that at the high temperature plateau, there is one laser beam that loses some power that we have to fix and to understand what is going on in this situation at 38 degrees or something like this. So a little zoom on the cesium clock, so I will not give you a tour of the operation of a cesium clock here, just to show you the geometry. On the left, you have the cold atom source, which is a cesium vapor, which are collected by laser beams. They are slowly launched at a velocity between 2 or 3 meters per second to about 10 centimeters per second into the tube. In microgravity, they will propagate just by expanding, thermally expanding at 1 microkelvin temperature. They will cross the copper cavity, make the 2 Ramsey interaction zones in this cavity, and then we have 2 detection beams which tell us in which atomic states the atoms are, and everything is pumped with a small ion pump shown to the right, and getter pumps, and the temperature is very well stabilized, and there are 3 layers of magnetic shields to make sure that the Earth's magnetic field does not introduce systematic offsets in the frequency of the Pharaoh clock. And so this is assessing the accuracy of the clock is particularly important because the redshift test that I was mentioning before will rely exclusively on the difference of frequency between the Pharaoh clock in space and other fountain clocks on the ground. It's not like with a elliptical orbit satellite where you modulate the redshift because you modulate the gravitational potential. Here the orbit is nearly circular. It goes down slightly over time, but so the accuracy of the redshift test that I will describe now will be based essentially on the accuracy of the cesium clock Pharaoh. So a few words on the gravitational shift. There has been quite a few recent experiments to measure the Einstein effect, the fact that a clock in a given gravitational potential does not tick at the same rate as another clock in a different gravitational potential. And since the famous Pound and Repka experiment in the Harvard Tower, a long time ago, this first test was done at 10% level. Then there were other measurements, and one of them being the recent one being the Tokyo Tower experiment by Katori et al. In Japan, where they have put an optical clock at the bottom of the Tokyo Tower, another clock at 450 meters elevation. And as this was an optical clock, they could measure very precisely the difference of frequency, which was 22 Hertz between ground and space. And this was a test of the redshift at about 10 to minus 4. There was also, I think the best test currently is the one that was done on the Galileo satellites, which were launched inappropriately on an elliptical orbit. And so the group in CERT and the group in Germany have used this modulation of the ellipticity of the clocks on board the Galileo satellite to make the most precise measurement today of the redshift by analyzing. This was published in 2018. And let me end up by just finalizing a very spectacular experiment done in Juni's group in Gila, Boulder, Colorado, in which they see now the redshift over a sample of a strontium atom, which is 1 millimeter high. So when you take the 500 micron top part of the cloud, atomic cloud, laser-cooled cloud, and the bottom part, 500 micron below, you find a different frequency. So this is just to show you the exquisite sensitivity of the optical clocks today. So this was a differential measurement, locally differential measurement. Nevertheless, it shows you that you have to take into account GR, even over a millimeter redshift scale here. But of course, to make a precision measurement, this was a 10% measurement. To make a precision measurement, the space environment is much better. And within ESAs, here you see the formula. So you have a clock at far distance, 400 kilometers, one clock on the ground. The clock on board the ISS is at potential U2, and the potential on the ground is at the potential U1. And the Einstein formula says that the difference, the ratio of the two frequencies, U2 over U1, is simply 1 plus U2 minus U1 divided by C squared. And you can re-express this potential difference as GH over C squared, where H is the distance between spacecraft and the ground, and G is the average value of the gravity acceleration along the orbit. And the value, when you put numbers into this, first of all, you find that this is a blue shift, that when you measure on the ground, the frequency of the space clock is higher than the frequency of the ground clock, and the effect is plus 4.5 10 to minus 11. And so with a clock at 1 part in 10 to minus 16, you can hope to make this test at a level of 2 parts per million. So this is a goal of the ESA's mission, to measure the redshift, the Einstein effect, with an improvement of about a factor of 10 with respect to the Galileo elliptical satellite test. And so here is a list of the science objectives which were revised recently during an ESA review. So I've described the first one is a redshift that I was described. Another interesting application of ESAs is a capacity to compare clocks on the ground at a frequency resolution of 10 to minus 17 over 3 or 4 days of averaging time, something that you cannot do with the standard GPS time transfer techniques. So we have developed the microwave link as a capacity to reach 10 to minus 17 in frequency comparison over a few days of measurements, and maybe 10 to minus 18 if everything operates as well as it should. The red cross shows one of the objectives that was proposed in the early phase of the project, but which has become less interesting because science has progressed, which is the anisotropy, potential anisotropy of the speed of light when you launch signal into different orientation, for instance, toward the Virgo clusters or somewhere away from that. And ESAs here would make an interesting comparison, but not at the state of the art. Nevertheless, there is a new objective that has come recently, which is a search for dark matter. And so I have no time to enter into details here, but you can search for potential dark matter by looking at the time variation of the fine structure constant. The fine structure constant is a dimensionless number, 1 over 137. And you may ask, why is this value, and is it stable in time? And it was Dirac, the famous physicist, who asked this question, in 1937. Are we sure that the fundamental constants of the universe, as we see them today, are the same as, when the universe was only 1 billion years old or not? And so you can reinterpret this type of measurement, changes of the fine structure constant or modulation of the fine structure constant as a search for light, ultralight, dark matter. So I have no time to enter into details in this direction. Nevertheless, it's a very interesting direction that will be explored by the ESA's mission. So here I show you the current stability of the fine structure constant as a function of time. You see that it is in the range of a few 10 to minus 19 per year, and the ratio of the electron mass to the proton mass is in the range of 3 10 to minus 17 per year. So there is no detected changes as a function of time, but of course if you detect some changes, this is really a revolution because you have to explain where it comes from, and of course theoreticians have a very large imagination, and many of the predictions, of theory like the dilaton and massless dilaton or axions or so do predict both violation of the equivalence principle and also variation of fundamental constants of physics. Then the last interesting application is noting the progress of the optical clocks. 3 minutes? Yes, I'm close to the end. You see on this graph the evolution of the accuracy of the cesium clocks in black, which flattens around 1 or 2 10 to the 16, and Farao is among this family. And you see in red the optical clocks. And you see that since the year 2010 or something like this, the stability of the optical clocks is going about 2 orders of magnitude, maybe between 2 and 3 orders of magnitude better than the microwave clocks, simply because in the visible part of the spectrum, the electromagnetic field oscillates much faster than in the microwave. This is as simple as that if everything is constant, apart from that. And so if the pendulum ticks much faster, then you can measure time intervals much faster. So it's easy to say, to realize it's more complex, but essentially this is where this 2 orders of magnitude gain is coming from. And so here, let me remind you that 1 centimeter, 10 to the 18 is 1 centimeter equivalent of the gravitational redshift of the Einstein effect. So you see immediately that these clocks actually will become potential sensors. And so this is a very interesting application. And so here ESA will bring essentially its contribution to the future redefinition of the second, and also to the what we call relativistic geodesy, in which you can measure by a totally different manner than Champ, Gaucher, Grace mission, the potential difference between 2 locations. Essentially, you measure the clock at position A and the clock at position B. You make a time transfer between those two, either by a fiber link or by the ESA's link, and you can hope to determine in a sort of absolute manner. You trust the redshift formula at a part per million or less, and then you do a gravimetry, geodesy with this. So it's a totally new tool, actually, to explore the Earth's potential and the variation of the Earth's potential with a glacier melting and everything. So it's a very interesting research direction to move forward. And so let me end by just showing you the ISS. We will launch April 2 as of today by SpaceX for a mission duration of 2.5 years, 6 months of commissioning phase, and 2 years of data acquisition in the science mode. Here you see the the picture of the Columbus module and the ESA's platform that I was describing at the beginning of this presentation. And so in summary, we are quite excited by this launch. We will make a new test of the redshift. ESA's will bring a global comparison of microwave and optical clocks on a worldwide basis. And eventually, one point that is important is that ultimately the use of clocks on the Earth will be limited by the Earth's fluctuations. if you have more water in the Vistule River here or less water, you will see an effect on the clock here. So you will probe the potential, but this potential is changing. And when you have tides, in Paris, for instance, the tides would mean a shift in the range of 10 to 17 for high tides and low tides. And so, of course, you could say I model the tides, but the modeling has some limits, some limitation. So it's very interesting, very tempting now to put the ultra-stable clocks in space in order to remove, when you move away from space, all these fluctuations are vastly reduced. And in a GPS satellite, those are in the range of 10 to minus 20. So we have plenty of time to make progress with clocks during these periods. And so ESA will be a sort of precursor from the Space Optical Clock project that will be described by Stefan tomorrow morning, and FOCUS, which is an equivalent project in the US under study. And so I finished. Let me just thank all the participants to this mission over the years. Here is a list of names and of institutes. And just rendezvous at Kennedy Space Center, April 2nd, to see the launch of Pharaoh by the SpaceX rocket. I thank you for your attention.
Thank you very much, Christophe. We have some time for questions. Maybe you can, yeah, thank you.
Oh, yes, thank you very much. That's really fascinating, and we're looking forward to the results. I wondered whether you take into account variation of the gravitational potential along the orbit due to, and how actually?
Essentially, what you probe is the average of the potential on the orbit. So you put the EGM model in the simulation and in the calculation, and the clock will experience. By the way, the clock, the ISS is going, the distance to Earth is changing with time. So this will change the redshift also. So you have to include all this. You have to have also, but this is measured by the orbitography of the ISS with enough precision. And so let me add that we need to compensate for the second-order Doppler effect, which is large, which is even larger than the redshift. But this is very well measured because you know where the ISS is with meter-type precision, essentially. So you make all this trajectography of the ISS, and from this you compute an expected redshift, and you compare to the measurement from space to ground.
Okay. Thank you.
Other questions?
Yes, thanks a lot for the talk. Same type of questions. So if you are saying that you are sampling basically the gravitation of masses on Earth around one orbit, how do you guarantee that this stays constant, basically, because you'd need that, right? Over orbits, over several
actually,
orbits.
it's not one orbit, it's many orbits. You do, the orbital period is 5,400 seconds. So you do almost 10 orbits per day, and we will average over 10 days, let's say, just to give order of magnitude. So you have 100 orbits that you will time average to measure the redshift. And so you will have the position and velocity at each part. And as I said, the Earth field fluctuations are negligible at this level. You see, the Earth can be considered as a solid body on average over this number of periods.
Okay. Thank you.
Maybe I take the chance on one last question, Christophe. If you can comment on applications of clocks and links for exploration.
Oh, yes. Well, exploration is a very wide subject. We heard about it today and also yesterday, but I was not there yesterday. It's obvious. For instance, people now are considering creating a GPS around the moon just to know where you are. And for this, you need precise time transfer. So we could use ESA's two-way time transfer as a direct instrument for making moon to satellite or Earth to moon. It would need some modification because the distance is much larger, but you can use the same principle to make precise time transfer between Earth and moon, or to make a connection between satellites around the moon. This is just one example for navigation. In exploration, if you go to Mars, which is much farther, also you will have to have precise time and timing between Earth and Mars, or Moon and Mars, of course, which can be done with the advanced microwave techniques that are developed within ESA's, and also in the optical range. If you have as you have less atmosphere between the Moon and Mars, you can use also optical links a la ELT that we are using here. So those are just two examples. Of course, you could, and we will see this in later talks. People are interested in developing, gravitational wave detectors on the Moon. Why not? It's a bit dusty there, so it will have to be dealt with. But okay, so that's a short answer, but we can discuss this in a longer at coffee break, if you wish.
Thank you very much, Christophe. Let's thank the speaker again. And I invite to come on stage the next speaker, Marco Muccino. Marco is from the Istituto Nazionale di Fisica Nucleare, and he will tell us about the MPAC experiment.
Okay, I think you can hear me. I hope so. So, yeah, just do. Okay. So, thank you for this occasion, for telling about. This is a payload, first actuated payload, having on it a lunar laser retroreflector that is called Moonlight. You will see later on. Do not mistake this acronym for the other Moonlight you have heard from yesterday. So, as I mentioned, this is a payload, and we fly with NASA CP11 mission. So, for this reason, beside the long list of collaborators from National Institute of Nuclear Physics, you can see there, I also put there in this slide the point of contacts from ESA, NASA, and also the Italian Space Agency, at least for concerning the part of laser ranging, because we have a joint lab with ASI Matera. So briefly, the outline of this talk is the following. So we are just, I think I will switch here because, can you hear me? Because I cannot see very well the slides from here. Sorry. So yeah, what I'm dealing with essentially is with weak field. So essentially the Earth-Moon system. So the measurement we are dealing with lunar laser ranging, a measurement of the distance between Earth and the Moon. And so we are in this weak field regime. So the situation so far is the following. So this measurement was done by decades using the Apollo retroreflectors, array of retroreflectors. There are 3 of them, and a lunocode, a couple of them on the Moon. So the aim for the next missions on the Moon will be to bring them there, the next generation lunar laser retroreflectors. And there are a couple of them, a couple of candidates, of course. The first one is Moonlight, as I mentioned before, which is a retroreflector integrated in the MPAC payload, ESA payload. And this will fly next year, the end of next year, now I can say, since yesterday was said. So we'll fly to Rainer Gamma Swirl on the Moon. And here you can see all the details regarding the contract. And Moonlight, finally, I can say that is a nice acronym for Moon, Laser Instrumentation for General Relativity Geophysics High Accuracy Tests. And There is another big retroreflector, next generation retroreflectors, which is called NGLR, Next Generation Lunar Retroreflector, straightforward acronym, developed by the University of Maryland. And this would fly on NASA mission called Ghost Blue mission at the beginning, I think at the end of the beginning of 24, 25 respectively. It's not, it will land to another site on the moon, Mare Crisium, which is opposite with respect to the Greiner Gamma swirl. So in principle, we have a large basis between these two next generation laser retroreflectors. That would be beneficial in the future. And so what we would like to do with essentially with the ESA Moonlight developed by INFN Frascati and also using NGLR would be to probe gravity through, fortunately there is here, I don't know if you can see, but this, that question mark was the parameterized post-Newtonian beta parameters, so the aim is to also give estimates on this, also to give estimates on the weak and strong fashion of the equivalence principle, and so on. So this is just a little bit of advertisement for at the SCF lab inside INFN. This is a facility that explicitly is devoted to design, test, and realize, and also eventually follow the laser ranging of many retroreflectors, single or arrays of them. In particular, you will see on the top left, you'll see Moonlight, which is the big retroreflector for lunar laser ranging. You will see also on the feet of this Moonlight, there is a micro-reflector, a small array of retroreflectors, which are a couple of them already on Mars, waiting for Mars orbiters, of course, and they are on ExoMars and Perseverance, but there is also one on the Moon on Chang'e 6. And you'll see also other applications, in particular the European Galileo second generation. You can see also geodetic satellite like LARES-2, and there is the aforementioned ASI-INFN joint lab for laser ranging operations. So effectively in this lab we can test and realize payloads having technology readiness level larger or equal to 7. So, okay, so, yeah, sorry. So finally we go to the core of this presentation. So the ESA payload called MPAC, which is another acronym that contains another acronym, is actually the Moonlight pointing actuator. So this payload is very simple but not so trivial. And you can see that starting from backward from the third block, you'll see that the Moonlight retroreflector is inside a housing, which is not labeled by number 3. And this housing is sustained by the number 2, which is the elevation frame, which enables rotations from 0 to 180 degrees. Of course, this is ideal range of rotation. And this is sustained on its turn by the azimuth frame, which is labeled by number 1. Again, this frame contains most of the electronics and enables rotations from 0 degrees to 180 degrees. As you can see in the picture, the 0 and the 180 extend degrees are labeled clearly. So this is the long story short. I don't want to repeat so many information, but essentially most of main informations are the following: that there was the call for launch by NASA initiative called Commercial Lunar Payload Service, CLIPS for short, with the payload and research investigation on the surface of the Moon, which is another nice acronym that is PRISM 1A, and altogether eventually they were merged together in the CP11. So later on, if you just read CP11, be aware that it means exactly this very long acronym naming these kind of missions. So the situation started in November 2021 when NASA awarded Intuitive Machines, a commercial company, to bring science payloads and demonstration instruments on the moon. And in particular, MPAC will be on the moon on the third mission, IM-3, on the Nova Sea lander. It will be integrated with other payloads. So the situation the exchange of information with IM, NASA, ESA, and INFN started in December 2021. And skipping all the details, eventually, in October 2nd, 3rd, in this couple of days, we brought to IM premises at Houston the first protoflight model of the impact payload, PFM-1. So the situation is still continuing because we have another protoflight model, the PFM-2, that was, okay, we are sustaining the Delta FAR in these months, couple of months, and will be very likely concluded at the end of this year. And the delivery of this second model will happen at the end of January. Unfortunately, I made a mistake, not PFM-1 delivery, but PFM-2 delivery. Yeah, the second one. Again, to IM premises at Houston. So the landing site will be, of course, as I mentioned, Reiner Gamma Swirl. These are the coordinates. So it's a magnetic anomaly close to the Reiner Gamma crater. The landing site is very fascinating and also very nice also from the point of view of lunar laser ranging, because there are no obstructing features there. So in principle, that helps a lot. And of course, launching date will be the end of 2025. So next slide. Probably is a little bit outdated, but it serves for my purpose, especially if you look at near-side CLIPS missions. So the ones labeled by 2 and 3 are respectively IM-3 and Firefly Blue Ghost mission #1 that will bring to the moon, respectively, MPAC and NGLR, so the two big retroreflector, next generation retroreflectors for the moon. And the other missions, of course, on the far side and the South Pole. Okay, this is another nice slide I collected, putting together the information of the delivery of the PFM-1. So the acceptance at ESA, first you see many personalities from ESA there, also our very happy faces. And you see also some pictures from the delivery to IM with the mass estimate, mass measurement of the payload, PFM-1, and some connectivity tests performed always with PFM-1. On the right side of the slide, I don't know if I can activate somehow the short movie. Yeah, there, thank you. So you can see and hear clear and loud some operations, the beginning of the test on the PFM-2. So this is part of the software test we were performing. Don't be scared by the noises, because there are, gearboxes inside metal frames, so these noises are resonating. That's the real cause of these noises. But these noises are like pulses. It means that the payload is alive and functioning. So those were software tests and full functional tests. Below you can see some pictures taken from ESA-HRE during the test campaign, in particular vibration test and TVT test. So yeah, we can stop the movie. Thank you. And yeah. Okay, yeah. Now let's go into the main part of this presentation, this talk. In particular, I want to prove you what is the situation and why a single retroreflector, big retroreflector, can work comparably or even better with respect to some of the existing arrays on the Moon. In particular, my comparison will focus on the Apollo retroreflector arrays. There you can see the comparison. The big retroreflector is Moonlight, and the smaller one are the many retroreflectors you have on the Apollo arrays. So the situation so far, thanks to Apollo, is depicted on the top left panel. In principle, we cannot go below at the moment of a few millimeters, 0.7 or 8 millimeters. This is mainly due to the fact that we have to deal with a phenomenon related to the inclination of the lunar orbit with respect to the ecliptic plane. So that is the lunar libration. So they limit the current accuracy we can provide for lunar laser ranging measurements. The fact is that the arrays have a physical dimension, and they are affected by libration. So in principle, you have, for some many configurations, you have some retroreflectors of the array which is farther or near with respect to the opposite corner, for instance. So, and this limits this measurement. Instead, with single retroreflectors like Moonlight, this situation, there's no more the case. And so, finally, one can exploit the full potential of the laser ranging stations, that they can fire pulses with width of 10, 20 picoseconds, and in principle, with the design of MPAC, Moonlight retroreflector, we can go down even lower to this 7, 8 millimeters. Of course, they will need some time, but let's say in the first years of activity, we'll for sure will go below this accuracy, unless there will pop out some other systematic effects. But even in that case, we'll be able to model them. So it's, in any case, it's a good achievement. But the main question probably will rise in your minds is the following. A single retroreflector can provide the same laser return of an array of 100, 300 retroreflectors? The answer is yes, because if you look at laser return intensities in terms of optical cross-section, and you just compare these optical cross-sections in the exact velocity aberration range on the landing site of the Moon, for instance, for MPAC, I mentioned is Rainer Gamma squared, but also for Mare Crisium would be more or less the same amount. Lunar, the velocity aberration with respect to the Moon and the laser ranging stations is of between 4 and 7, let's even say 8 microradian. So if you compare these optical cross-sections, the top one is for one Apollo retroreflector and the bottom one is from Moonlight, you will see that more or less the optical cross-section for Apollo retroreflectors is 10. For Moonlight is of the order 200. So if you multiply the top for times 100, 300, you get a larger number, which is of the order 1,000 or 3,000. But you have to take into account that nowadays the arrays are obscured by the dust deposition. They retroreflect 1/10 of the initial returns. So if you take into account this effect, you also model the thermal degradations, but the amount is of the order of 0.8. Unfortunately, that was a zeta letter. You cannot see the red question mark is a zeta letter. So if you do the ratio of the laser return intensities, you see that they are comparable with or without the thermal effects. So in principle, yes, Moonlight provides laser returns comparable with the arrays. And so the main point now is that we have to point exactly Moonlight toward the Earth, and you have to take into account, of course, also libration pattern. So you have to take into account, as you can see in the bottom plot, that the Earth is not always in the same place because of libration. So in principle, the best strategy would be to point at the center of the libration pattern, you see there, and on average, you will point toward the Earth direction. In order to do so, since there's no way for the lander to activate MPAC or move MPAC, Moonlight, we use the asset of the impact payload, so the dual equator. So the goal is to point within 3 degrees, because if we are misaligned, of course, there is a reduction in laser returns. So with an accuracy of 3 degrees, if we are misaligned of 3 degrees, at most we lose 12% of laser returns. And so if you do the math again, take into account this effect, you are still, you get still comparable ratios over there. So still laser returns are comparable if we stay within these 3 degrees. So the operations will be the following. The simplified concept of operation is the following. So we deal mainly with 2 cases, nominal landing and actual landing. The landing stays on the lander reference system. So if the lander lands as nominally, so as declared, MPAC in its reference system will just point to the nominal Earth direction and will be launched already in this position. So the mission is accomplished. We have to do nothing actually, because the landing nominal Earth direction is already there, is computed, can change a little bit depending on the launch date. That will be refined later on, but the mission, the goal mission is achieved at that point, yes. With the actual landing, we have to take into account that we have to transform into the payload reference system and compute actual Earth direction. That is still TBD, of course. It depends on how the lander will land, of course. So depending on this, we have 2 scenarios or 2 plans. Like myself, I have this dress here for the conference, but on the occurrence I have these shoes, because I didn't know initially if there was snow or heavy rain, so that's why I have these shoes. So 2 plans. Scenario A is the simplest one, in the sense that if the lander lands correctly, MPAC is already pointing, so laser ranging station will fire laser pulses to MPAC, mission accomplished, because in principle everything is okay. If it is not the case, it means that there will be the actual landing. So we have to interrogate power on MPAC, ask where it is, reading the status reply, just computing the actual Earth direction, point MPAC toward that direction, and eventually ask a status reply. And after that, of course, we ask laser ranging stations to verify laser returns. Of course, there could be some occurrences for which we don't see laser return. So we plan to do a scan, moving of delta azimuth, delta elevation, and see with the aid of laser ranging stations where the laser returns are achieved. Of course, this would be a longer operation, a longer also data rate budget, but not so much, as you can see in the bottom part of this slide, that is very limited amount of data rate. So fundamental physics with MPAC. So we can probe gravity. We can test equivalence principle thanks to the the range measurement. We can test variation of the gravitational constant, and also perform tests of GR or beyond GR models. For instance, evaluating the ppm parameter beta, which is still there, the question mark, you cannot see there. And the situation is exemplified by this table. So the second column actually is the current situation. So we are a few centimeters, but in principle you can go down to 1 centimeter or 8 millimeters. So the situation is exemplified by the first column. With the next generation retroreflectors, the situation will change. In the first years, let's say you get laser range accuracies of 1 millimeter. So in principle, all these accuracies on weak, strong equivalence principle, beta, G dot over G, geodetic precession, and deviation in Yukawa-like potential, deviation from 1 over R low, can be lowered by 1 order of magnitude. And with time scale of some years, 5 to 10 years, in principle, one can achieve even the 0.1 millimeter accuracy and further lower these limits. And of course, we were also working on this in INFN. In particular, I show one of the recent papers were published on constraints of non-minimal coupled gravity theory within lunar laser ranging data. But this is one of the many papers published. So in 10 years, there are many papers using laser ranging, not only lunar laser ranging, but also satellite laser ranging, but also applications all over the solar system, just to, for the sake of giving some insights in fundamental physics. So you can see here on this list. But yeah, the goals will not only be on fundamental physics, also geophysical science will benefit of next generation lunar laser retroreflectors, because first of all, these retroreflectors would be kind of fixed points on the surface of the moon. So if you just join big retroreflectors with smaller retroreflectors that can be laser ranged by orbiters, in principle, one can improve in the for the next future, can improve also selenodesy on the moon, having some reference points on the surface of the moon. But don't forget that MPAC, so moonlight, will be able also to reduce, or even cancel out the libration effect. And lunar laser ranging measurements up to date are affected by these effects. And librations are connected to the interior structure of the moon. So in principle, with the next generation retroreflectors, if we can single out this effect, we can better model this libration and better provide better models also for the interior of the moon. So this is also another asset. So this is the conclusion. So in conclusion, yeah, there will be benefits not only for fundamental physics in the sense of beta parameters estimates, test of equivalence principle, but there will be also benefits for lunar geodesy and lunar geophysics. And with future missions, with more possible impacts, this will, of course, increase in importance and in magnitude. And last mention is that eventually this, let's say, MPAC and moonlight can be also used for future gravitational wave detection on the moon, because it can, in principle, work instead of a mirror, which requires a precise orientation toward the laser. Retroreflectors are not so picky. So in principle, you can do it within the 3 degrees declared accuracy, as I mentioned before. So back slide, just to, I show you briefly, just to support some further questions or comments on it. But this is the end of my presentation, so thank you all for the attention.
Thank you very much, Marco. We have time for questions.
Hi, thank you for that presentation. I have 2 questions. You mentioned the effect of dust on the old reflectors that are up there. Is there anything on moonlight that will reduce the effect of dust, or it will just build up?
No, for the payload now as it is, no. There were some, there were some consideration using dust cover, but essentially the problem still stays, because after landing the dust floats for even years. So in principle, this effect is unavoidable. So what I was saying about any kind of measurement or limit for the constraints of the, I showed before, refer, of course, along a limited amount of time, because, you know, eventually also moonlight will have the same destiny.
It's a factor of 2 over 10 years.
Yeah. Yeah, we have to wait for 16 years to have a reduction 90%, yes.
And can I ask a second question? Yeah, just the very last thing you mentioned about gravitational wave detectors. So the mirror that exists now, is it already sufficiently stable and so on to be immediately useful for a gravitational wave detector? Or
Stable, yes. The only instability that could be for this retroreflector are thermal effects. Thermal effects affect a lot the far-field diffraction pattern from these retroreflectors, also the laser return. But in principle, if you work in a stable thermal environment, for instance, during the lunar night when there is no sun, it's very stable. I mean, of course, we'll experience dust deposition and so on, but in principle, it's stable. And as I mentioned, the reduction in laser return will be not so much if you limit your misalignment, let's say, of 3 degrees. But in principle, you want to do better, so there will not be super much problems.
So back to the fundamental physics tests. So do I understand correctly that the performance of the tests is limited by statistics in the end?
Yeah, so if you have seen the 3 columns showing the evolution of the limits with time, yes, initially, yes. We have just 1 or 2 next generation retroreflectors. We have, yes, 3 Apollos and 2 lunokhds, but in order to reduce and go to regime, you need statistics. But already 1 or 2 of the next retroreflectors, next generation retroreflectors will do the difference because they will mostly be unaffected by libration. So if you want to further go down, at that moment you need statistics, yes. So in that case you will reach essentially the end of plateaus in that case, but the big difference would be in the first years. Yeah.
Okay, let's thank Marco again. And the next speaker is Jan Arns from the Gran Sasso Science Institute. And Jan will tell us about the lunar gravitational wave antenna.
Thank you, Luigi. Okay, yes. Un attimo. Okay. So indeed, some people want to do gravitational wave detection on the moon, and there are, in fact, different ideas how to do it. And that is maybe something to sort out as well. But yeah, I will represent one of these ideas, and it is a proposal that we made as an idea submission in 2020. And well, it's proceeding. So let's see. Maybe is that the one? Okay. So maybe first, quick warm-up what gravitational waves are. I guess most of you actually know, but so what you will see here is a video, and the 2 black dots are represent 2 black holes. And the green field is representing space-time curvature, and that is what this system is emitting into space.
Form of gravitational waves, ripples in the very fabric of space.
Okay. I didn't know that there was a sound.
Constantly draining energy from the black hole.
So, well, I let him speak. I didn't know that there's a sound. The thing is the following. These merge, and at the end of their lifetime, when they merge, they send out the highest frequency signals into space. Once they are out, they're propagating without being hindered by any matter, essentially, negligibly at least. And then at some point they come to Earth, and what happens is that Earth wobbles. It's an elastic body that responds like a bell to this space-time fluctuation that is propagating through it. Now, in fact, the very first gravitational wave measurement that was ever done by Joe Weber and seismologists in Caltech was trying to see that wobble in data, and that was in the 60s already. So, and then, of course, Weber understood very well, very soon, that Earth is too noisy. Today, we can track this down really to the atmosphere and the oceans. These are the 2 main contestants here. Human beings and earthquakes are a factor as well, but much less important. Why? Because what we are really worried about is the continuous noise background that you always have. and that is produced by atmosphere and ocean. So already at that time, he must have gotten the idea then to proceed with the next idea. And so this is connected to the lunar gravitation wave antenna. So what we proposed in 2020 then is to do the same idea, but on the moon. And essentially what we then want to observe is this quadrupolar wobble of the moon produced by gravitational waves. And so all you need is, in principle, one compact sensor on the surface to measure these vibrations. It's not this long baseline concept that you know from LIGO Virgo. Now, what you see here on the sketch is essentially an array of 4 seismic stations in a kilometer scale array. So the detail of how big this has to be depends on the properties of at the site there. And it is located in the permanently shadowed region. So this is one big change that we made early on, because what we need is very good thermal stability to be able to do that. So there were observations made with the Apollo seismometers showing that thermal effects add a lot of excess noise to the seismic data. And so we need to avoid that. So it was very clear that we have to do this in a PSR. So just, this laser field that you see there is not part of the measurement. It is meant as a proposal how you could power such an experiment, because you don't want to keep this alive for a few months. This should run for many years if possible. And so that is, of course, a huge challenge. So it's also cold there. It's not only thermally more stable than the rest of the lunar surface, it's also cold, which is another benefit for us when it comes to the instrumentation, which operates better at lower temperature. And then here you see NASA Apollo 17. So there was already a gravitation wave detector on the moon. The basic idea behind all of that is old, as I said, and Weber himself was the PI of the lunar surface gravimeter that was deployed in 1972 with Apollo 17 to measure gravitation waves. That didn't work out for a few reasons, and one of the reasons was essentially technology, which was not at the level that you need. Okay, but now the other really big reason, it's not only the PSR that is helpful, but generally the moon is known to be seismically extremely quiet. We don't really know how quiet it is, because the lunar seismometers, even though they were excellent technologies, were not able to see the continuous seismic background. So they were able only to set an upper limit on that background. What was observed, of course, were numerous moonquakes. And of course, they have been studied. But this is not what bothers us really. We have to think about what is the continuous seismic vibration that is always present on the moon. And so we have only models at this point. There were people predicting from meteoroid impact essentially a hum that is at the tens of femtometer level. And that would be low enough for gravitation wave detection. But we don't really know. We have certainly, first of all, improve our models, and then, of course, if possible, have new data from the moon. But we are speculating, based on the models we have, that the moon is, in amplitude, 7 orders of magnitude quieter than Earth. And that enables the whole thing, of course. Since we're interested about the seismic background, there are also very interesting things that we have to take into account, like, for example, the fact that the meteoroid impacts are not uniform across the lunar surface. There is for sure a strong dependence on the latitude, so the equatorial regions are more impacted than the polar regions, and that has to do with how these particles move in the solar system. Also models confirm these measurements, because in the measurements there could also be, these are essentially flash observations from impacts. There could also be an observation selection effect in there, but even the models clearly say, okay, if you're at the poles, you should expect a lower impact rate, and that of course leads to a lower seismic background at the poles. And there might even be a north-south asymmetry here. People are finding evidence that the north has maybe a higher impact rate than the south. So these are the details that really matter to us, because they can give us more sensitivity in the end to gravitational wave measurements. So things that we have to understand better. So you start to see that this is really a very strong connection between gravitational wave detection and lunar science. And in fact, now the key is, how exactly does the moon respond to gravitational waves? And we have to understand the deep internal structure. We also have to understand the geology and topography at the deployment site of the experiment. And all of that goes into the response measurement. Now, you see in the graph there essentially how such a model can look like from 1 millihertz to 1 hertz. You see that it has many peaks in the response spectrum, and this essentially comes because there are resonances. Again, the quadrupolar modes have their resonances at certain frequencies, and that's the spectrum that you see forming here. Some of these peaks might have a height of, Q factors of hundreds. But even that we don't really know very well today how this exactly looks like. Now you might think, okay, but if you want to do gravitational wave science, if you know LIGO Virgo, if you know LISA, then you know that they try to calibrate their data to within fractions of percent, LISA even much better, and that's how they get very good science out of their data. So you might think like, okay, but with a lunar detector, how could you ever know the geology and the internal structure at the percent level or even better to get all the information out of your data? So there's a trick that we will do. So first of all, observing gravitational waves over many years, you will be able to gradually improve your response model. But there's something even better. For example, some of the sources we will be able to observe not only with LGWA, but also with LISA, if LISA were, or LISA type detector, or terrestrial detectors. So what that means is the terrestrial detector makes the observation, and then we get a very precise calibration of that signal to LGWA frequencies. And essentially, we use the calibration of ground-based detectors to calibrate our own response very accurately. And this is a multi-band observation that we are exploiting. And then in vice versa, what this means is that we can do percent-level geology or geological studies, internal structure studies at the percent level using gravitational waves to make a lunar tomography. So this is mind-boggling because that is the first practical use probably that anybody ever suggested for gravitational waves. But we can do that, okay? So we will have a tomography here. Good. Now, but since there are so many question marks, we need a Pathfinder mission. And so what we then suggested in 22, I think, we proposed soundcheck. Soundcheck is a much simpler thing. It is a single station with the complication that it still has to go into a PSR. We cannot measure really anywhere else because we do expect a strong difference in seismic background between PSR and any other region on the moon. So for that reason, we are kind of constrained to go there, and that, of course, adds a bit of complexity to this thing. But otherwise, it's much easier, also because the lifetime of that mission can be in the month instead of years. And so you can hope maybe to operate with battery if your power consumption is low enough. And so that is the planning. And then, of course, what we need to get out is a lot of geophysical information. We want to observe many moonquakes to understand more the geology at the South Pole. We have to understand temperature fluctuations, magnetic fluctuations, and hopefully, even though while the sensitivity of the accelerometer will be much better than what Apollo instruments had, soundcheck will still not be enough to see the seismic background. So we can only what we can do is to observe moonquakes at lower and lower magnitude, and then essentially try to see the distribution of these events and maybe extend to a point that we can infer the seismic background that is always present. So this is a little bit the game that we want to do with that. And of course, it's going to be a technology demonstration as well, because the sensor design will be quite similar to what we want to do with LGWA. Now, we have started to work. So in fact, we have around 10 groups in Asia and in Europe working right now on the payload, realizing components. We have thin film, niobium nitride actuators that are being coils that are being prototyped with India, Unicamerino, and Max Planck Institute in Germany. We are working on the high precision laser interferometric readout, so it has to be a quantum limited kind of readout, of course. And we have in Twente, we have a group working on the sorption cryocooler, which is needed for LGWA. So because since we want to use superconductors, we have to go to even lower temperature than what the PSR provides. So we are looking into low vibration cooling methods. And then all of that has to come with a facility that we can use to actually demonstrate the performance of all of that. And that is really the tricky part. because the moon is so much quieter than Earth. The question is, how would you ever be able to even closely demonstrate the performance of these sensors? And so what we are doing, and I just received deliveries last week. We will, more than a kilometer underground, build in Italy, in Gran Sasso, a test facility, platforms that have a diameter of 2 meters, 2 of them essentially. And then these, so there's already a very quiet, seismically quiet environment. We will then further stabilize them actively with seismometers. So these will be seismically stabilized platforms. And then on these platforms, we will put the sensors that we want to send to the moon. And not only will this be vibrationally very quiet on these platforms, but also we have a cryogenic system so that we can emulate the thermal environment of the PSR. And so the payloads can be tested on these platforms at the right temperature and at a vibration level that is at least getting to within some orders of magnitude to what we have on the moon. And then you can play tricks to actually perform, to actually measure the real performance. Okay. So things are happening, so people are also building the mechanical structure already, and this is proceeding. Now, what actually is the science that we want to get out of this? And it turns out there is a big science case for gravitational waves. So this is the story left, you have to think about this in terms of frequency. So LISA will observe millihertz, up to tens of millihertz maybe signals, also below millihertz. Terrestrial detectors will go to maybe down to a few hertz in the future with Einstein telescope. Now that leaves a gap between LISA and the terrestrial detectors. And it turns out that this is a particularly rich band. And we have known this forever because NASA made studies in the 90s already to say, like, okay, what technology can we do to make observations in that band? It turns out to be very, very hard. So there's a reason why we are not covering it yet, because it's really hard. And the lunar gravitational wave antenna is one of these ideas that could really give us observations in that band. And so there's a specific mass range of binary black holes that we will be able to observe to high redshift. We will have Newton star disruptions, tidal disruptions, white dwarf tidal disruptions, so white dwarf mergers. These are all events that only happen in that band. So LISA is not going to see it, terrestrial detectors are not going to see it. Okay, so let's look a little bit more into that. So again, so here in blue, you see like the sensitivity curve essentially of LWA. Of course, with some question marks, because it does depend on things that we don't know very well, like how exactly what exactly the geology is at the site and so on and so forth. But take this as a guideline. This is a reasonable model for sure. And so here you can see also traces of some signals. What you can see is that, for example, Newton star binary will first be observed with LWA months before the merger, and we will, with LWA, be able to give a very precise sky localization within, square degree, sub-square degree. And so we give a warning to electromagnetic observatories that there will be a merger at that location. So the we don't need warnings for ground-based gravitational wave detectors, because once it is in their band, they will see it as well. But the very early warning is, with this calculation, is extremely helpful for all the electromagnetic observatories that can then point to weak emissions from that source. For example, but also if we had a LISA-type detector online at the same time, then we could observe certain massive black hole binaries together and do much more precise analyses of the waveforms and the sources. So there's this multi-band observations becoming a huge game with a detector in that frequency band. Okay. Now, generally, you could also say this the LWA will be a detector of stellar disruptions and explosions with gravitational waves. For example, disruptions of Newton stars when they plunge into a black hole, or a white dwarf plunging into a black hole. Two white dwarfs merging will initially tidally disrupt, and then they will merge. Then there's the question, what is the progenitor of type 1a supernovae? We don't know. People say it might be a merger of two white dwarf binaries, or it might be one white dwarf accreting mass from a companion star. So we don't really know what the story is. We will be able to answer that with LWA. Even core collapse supernova, which we typically understand as high-frequency emissions in the hundreds of hertz, they also, we know, emit a quite strong, peculiar low-frequency gravitational wave signal, which we call gravitational wave memory effect. And that will be detectable with LGWA as well. So there's a lot of multi-messenger physics here with electromagnetic observatories, because tidal disruptions, of course, are already being observed. And so, I think this is really creating a lot of richness in the science case. If you, and this, I'm already coming to my last slide, if you want to know anything more about the science case, at the moment you will find only on arXiv, very soon also in JCAP, this science white paper where we summarize the science that we think we can do with LGWA data, which is lunar science and gravitational wave science, but also has a section on what is the science that we need to do and what do we need to understand about the moon before we can even plan accurately LGWA as a mission. Because with, we have to address many questions and answer things that we cannot do today. Luckily, of course, lunar exploration will provide a wealth of data in the coming years, and this is all data that we are going to look at for sure. But then with soundcheck, I hope that the last question marks can be filled. And so here I want to stop. Thank you.
Thank you very much, Jan. Questions? Let's start. Go ahead.
Okay, sorry. I have two questions actually, but the first one I'm ashamed of. I'm not sure I understood how you measure them. You're not doing interferometry, so is it purely acceleration?
So yeah, so you have essentially in a mechanical structure, you have like a suspended test mass, and now when the ground moves, and it's like a seismometer, essentially then the suspended mass moves against the frame, and this will be read out, but then again a laser. But there's, of course, it's a very compact laser interferometer that you just integrate in this payload.
Okay, and the second thing is about removing noise. You mentioned seismic noise. Can you use the fact that you have several different detectors, and if you see the same type of signal, with some propagation, which is, I don't know what's the velocity of the seismic wave, but of course much smaller than.
So this is the reason why LGWA is proposed with 4 stations, because if we just wanted to see gravitational waves, 1 station would be enough. But then we still anticipate that there will be a limitation from the seismic background. So what you then want to do is you want to use the array, because the gravitational wave signal will be common throughout the array, exactly identical, but it will be different for the seismic background, where you have the waves propagating horizontally mostly, but at some angle anyway, and so you can use phase differences to distinguish between the two and reduce post-processing-wise the background.
So it's a veto, essentially.
Yes, because we don't want to rely only on models. We need a handle to actually, somehow make it work with the technology.
Yes, well, my question builds up on the previous one. So how do you get the sensitivity that you are quoting here? And how do you get the directivity that we are mentioning,
yes.
in the sky?
Two excellent questions. So maybe first the sensitivity. So what we need in terms of displacement sensitivity is between a picometer at 0.1 hertz to a femtometer at 1 hertz. So that is the sensitivity that we need in displacement. And that is really not so easy. And there are but we have the groups working with us, LISA Pathfinder, has already achieved tens of femtometer. And the same groups are working with us to get it to a femtometer. And so the path is clear. So, but anyway, so LGWA is really quite challenging to get the sensitivity, femtometer. But then, of course, the baseline that we have effectively, which are the 3-4 kilometers that you have in LIGO, is when you think about the moon, the effective baseline is the length of the seismic shear waves, actually, it turns out. So when you want to make an order of magnitude estimate, then it is often, you can just say like, okay, I take the length of a seismic shear wave at a certain frequency, and that is effectively the baseline of my detector. And so then you can turn this into a strain sensitivity. Then you have to include furthermore resonant effects in the response, which there are because of layering of the geology, or even waves that go to the other side of the moon and come back again. So there are different ways to create resonances, but basically that's the story. Now for the pointing accuracy, that's the same trick that LISA is doing. So LISA is moving while it observes the signal. That leads to phase and amplitude modulation in your data. And so you can use that to point to the source. And we can do that with Moon as well. That has a rotation of once per month. But actually it turns out that the Moon, what actually gives us most of the skyrockerization is the motion of the Earth-Moon system around the Sun. Even for a few months, it's already enough because essentially the radius is so large and the distance you travel so large in a few months with the Earth-Moon system that this is giving you the dominant Doppler shift and amplitude change, and then allows you to point to a source.
But for this, you need to observe for a month or several months. Right?
It doesn't work for the more massive black hole binaries, which will be very short in our data. But when it comes to solar mass stuff or white dwarfs, it's all like years of observation.
Okay. Okay. Thank you.
Any other questions? Yes, please.
No, this one. Does it work? Okay. Sorry, I have a last question. So I'm more of a planetary science person. So I quite like to have units, these kind of things. Like, so you said you could do lunar geology and interior of the moon within 1% accuracy. So in terms of meters, kilometers, what kind of order of magnitude are we talking about here?
Yes. So that you could see it as you have to start from essentially from the station. So the finer resolution in space you have, the closer you are to the station where you deploy. Mm-hmm. So that means when it's about the deep internal structure, you will have the least resolution, spatial resolution. So in the near surface structure, you will have high resolution. So let me give you some numbers. So I would say like at 0.3 hertz or something like that, you would have then a resolution of a few hundred meters.
Okay, I mean that's already quite good for what we have. And also, like in terms of density, would you be able to like tell the difference between the different layers in like a gram per cubic centimeter? What type of also precision are we talking about here?
Well, I would have to think about it. I think you don't have a direct handle on the density because often the response comes in certain combinations. That means like I think if you construct a concise model that is valid for, when you kind of have a model that describes the response of the moon across the whole band, then I think you might be able to get out certain parameters additionally. But for example, I think the density comes not as a separate parameter that you can measure, but it comes in combination with shear modulus or something like that. So this is then the trick that, I think it probably requires some more sophisticated analyses from different frequency bands to be able to say something about, density or so.
But you would see like the difference in like physical properties between the different layers.
Yeah.
So even though you cannot directly
yes, that is true.
Out. Okay.
That is true.
Thank you very much.
Thank you.
Thank you. Maybe time for another question. Okay, then let's thank Jan again. And thanks also to all the speakers. We can close the session in time for the coffee break.